Hi, in this video I'm going to talk about Merkle trees. We'll see binary tree concept to be able to understand Merkle trees, Merkle root, and how does Merkle proof work on blockchain. So let us start with binary tree. A binary tree is a tree structure in which each node has at most two children. Binary trees can be used to represent hierarchical structures and to evaluate mathematical expressions. They can also have many other applications, such as implementing search algorithms. So here we have a root, and this root can have at most two children called branches. And these branches can have children called other branches. If the branches do not have any children, these are called leaves. Why is binary tree concept is important? When searching for a specific element in a linear list, it's necessary to look at each element one by one until the desired element is found. This can be a slow process, especially for large lists, as the search must look at every element in the worst case. For example, here, when you look for the element 32, you need to go over the list one by one to be able to find this value. But when it comes to binary search tree, which is a special type of binary tree, there is something different. So let's first understand binary search tree. A binary search tree is a type of binary tree that is used to implement search algorithms. Here, instead of having elements randomly, we have a different structure. A binary search tree is a tree where the left child of a node has a value smaller than the node's value, and the right child has a value larger than the node's value. Here, for example, for 8, we can see that all the right values are larger than 8, like 12, 10, 14, and so on. And when you look at the left side of the tree, all the values are smaller than the value 8. Okay, so this allows for fast search operations, as it is possible to eliminate half of the tree at each step of the search by comparing the search key to the value of the current node. So let us understand it in detail. For example, you are looking for the value 14. So you are asking this question: is 14 larger than 8 or smaller than 8? Your answer is larger than 8. Then you don't need to check these values. You only need to check these values. When it comes to 12, you ask the same question: is 14 larger than 12 or smaller than 12? Your answer is larger than 12. This means you don't need you need to check these values. You don't need to check these left side of the tree. So you don't need these values as well. In this regard, you have reached the 14 in 2 trials, which is great. In a linear list, you should have searched for the values at least 14 times if it's a list of increasing values. But here, we're using binary search tree, we got rid of this problem. But what we have done here, now I don't need to check these values, also these values, and I got rid of all of these values to check them, which is very important. All right, okay, let us understand Merkle tree. A Merkle tree is a tree-like data structure using cryptography to provide a secure way of verifying the integrity of large amounts of data. The main difference is that we basically use hashes instead of numbers. In a blockchain, transactions are hashed into a Merkle tree with the root hash included in the block header. For example, we have the text BNB chain, and we hashed it using SHA-256 hashing algorithm, and we got this hash value. You can also find it using this algorithm. So also for Patika, we got this hash value, and we grouped them into pairs to get a Merkle root. Then we can store it in our block header, and this is our Merkle root. We just hash these values. We can write them one after the other and get this value. Okay, this allows for the efficient verification of the integrity of the blockchain without requiring the transmission of the entire chain. So what do we mean by that? Okay, we'll understand this in detail by giving an example, but first, why do we need this tree structure? Let us understand this. Merkle trees are used in the Bitcoin blockchain to provide a secure way of verifying the integrity of blocks of transactions. Without the use of Merkle trees, it would be necessary to transmit and store the entire block in order to verify the transaction it contains. This would be inefficient and would require a lot of bandwidth and storage space, as the Bitcoin blockchain is currently over 400 gigabytes in size. Here is a statistic from 2009 to 2022, and it's the storage of Bitcoin blockchain, and it's increasing every single day. So imagine imagine storing all of the hash values instead of storing Merkle root. It's going to cost us a lot. Okay, let us give an example. We have seen this animation before. Now we have a Merkle root, but I forgot whether I wrote Patika.dev or Patika. I only have my Merkle root. I will first try BNB chain by putting it in the SHA-256 algorithm, and I will get this hash. Then I will put Patika.dev. I will get this hash. So when I got these hashes, I will write them one after the other, and I will get this Merkle root. So what I see, it's not the same Merkle root with the one I have in my block header, which is this Merkle root hash, meaning that it's not Patika.dev. So when I check for the Patika, I am getting this Merkle root from the combination of these two hashes. And now I can say that, okay, from Patika and BNB chain, I've got this Merkle root, and it is the same the one I have in my block header, meaning that, okay, the data is not changed. It is Patika instead of Patika.dev. Okay, so how does blockchain use Merkle tree? In a blockchain, each block of transactions is hashed, and the hashes are arranged in a tree structure called a Merkle tree. The root hash of this tree is then included in the block's header, allowing the integrity of the transactions in the block to be verified without the need to transmit the entire block, which is very important. We don't want to transmit the entire block. When a new block is added to the chain, the root hash of the previous block's Merkle tree is included in the header of the new block. This creates a chain of root hashes, with each block's root hash depending on the root hashes of the blocks before it. By using Merkle trees, it's possible to efficiently verify integrity of the transactions in a block and the entire blockchain, as it is only necessary to compare the root hashes of the blocks. So what we got here is the Merkle proof actually. We have tried Patika.dev and Patika to check the right Merkle root. And in that regard, BNB chain was our Merkle proof because it was the value that was not changed. Alright. So how does Merkle proof work on blockchain? When a node wants to confirm that a specific transaction is a part of a block, it can request a Merkle proof from another node. For example, in this regard, in one of the nodes, we know that the transaction is changed, but there are a lot of nodes, meaning that we can fetch information from one of them and check if there's a problem about our Merkle root. This proof is a series of hashes that form a path from the root of the block's Merkle tree down to the transaction in question. The node can then use these hashes to recreate the block's Merkle tree and check that the transaction is indeed included in it. If the transaction is included, the root hash of the reconstructed tree will match the root hash stored in the block header. This allows the node to verify the transaction in the block without having to transmit the entire block, which is very important. So that's gonna do it for this video. I will see you in the next one.